Hello, Honors Chemistry, and welcome to your Chapter 11 review. Obviously, so this chapter has a lot of qualitative stuff, right? Mixed with a lot of math. So do make sure that you go back through and you review all the qualitative stuff and that you know you're comfortable with what's in there, okay? So yes, like it says, review the qual stuff. KMT, don't forget you do need to have those principles memorized because every qualitative question is going to require you to be able to use those principles. Okay. So in summary, in very shortened summary, right? Particles are always moving in constant straight line motion. Those particles experience no interactions, right? No attractions, no repulsions, right? Not which is not true in real life, right? And their collisions are all elastic, meaning that energy is transferred completely with no loss, right? And tiny particles, well, the particles are tiny in comparison to the ginormous amount of space between them, right? And their kinetic energy on average is proportional to temperature in Kelvin. Ooh, temperature in Kelvin. Okay. All right, so make sure you have those memorized because, like I said, you'll apply them to every short answer question, right? So equations that you need to know, right? So like we talked about, there's the ideal gas law, which says PV equals nRT, which, like the name states, applies to ideal behaving gases, right? So obviously, a gas is more ideal, right, if it falls in line with these assumptions we make about gas behavior in KMT. We can also impose conditions on a gas, like low pressure and high temperature, to make it behave more ideally, right? Because low pressure, high temperature help to simulate these conditions for any gas, okay? So moving along, the ideal gas law is PV equals nRT, right? And again, bearing in mind the fact that R is constant, right? Make sure you know all of its units, right? Moles times Kelvin, right? Because R is constant, we can take this and rearrange this to say PV over NT is equal to R, right? Which means that P1V1 over N1T1 is equal to P2V2 over N2T2. Yes? Because if all of this has to equal a constant, then the second set would equal that same constant, which means they equal each other. Yes? Substitution. Math. But the fun kind of math, right? The kind of math that is very sensible and very logical. So anyway, so here we have this, right? Which means that if we think about this, this is all of our gas laws, right? We have our Boyle's gas law for pressure and volume. We have volume and temperature for Charles, right? We have volume and moles for Avogadro, right? And we can even define a pressure and temperature or pressure and moles, for example. Again, bearing in mind what? Right, the assumption is whichever things are changing, those 2 or 3 variables, right? The other ones must be constant, okay? The other ones must be constant or we can't apply it, right? Because they are all interrelated, right? So if something is not constant, we cannot compare. So anyway, we have this, and if something is constant on both sides, that cancels, and that gives us the rest of what we're looking for. Yes? All right, so again, we can derive everything from the ideal gas law, or we can just memorize them all, whatever floats your boat. Don't forget we have the derivation of the ideal gas law, wherein we can substitute or do some substituting with N, and we can get molar mass is equal to density times R times T over pressure as a derivation of this, right? These go hand in hand. In addition, the only one that is unique and different is Dalton's law of partial pressures, which states that, right, we can take the sum of my gases, right, so the partial pressure of A plus B plus C plus whatever is going to give me my pressure total, yes, which goes back to the fact that there are no interactions, which means that they're all floating around in the same space, right? And pressure is the result of collisions with the containers, right? So if they're not interacting with each other, we can take all the collisions of A, and that's the pressure of A. We can take collisions of B, and that's the pressure of B, etc. All of that together gives us the total pressure exerted inside of a vessel. Okay. We can also, looking at this from a different point of view, we can say that the partial pressure of substance A is equal to the mole fraction of A times pressure total. Yes? As in the pressure of 1 over the pressure of the whole gives me my mole fraction, right? Where mole fraction is a unitless quantity, right? That is moles of A over total moles. Yes? Going back to things we should know. Okay. So let's go ahead and start a couple of practice problems. So here it says, explain the relationship between pressure and temperature at the particle level. This relationship is also known as Gay-Lussac's law. So your book doesn't cover this one because, you have to pick and choose, right? So explain the relationship between pressure and temperature. So first, it might benefit us to think about what the relationship is mathematically before we try to explain it qualitatively to make sure we're doing it right? So if we go back one page, we'll see that pressure and temperature, use a different color, right? Pressure and temperature have what kind of relationship? Right, it's one on top of the other has to equal a constant, which means that if one goes up, the other one must, right, go up, which means that they have a direct relationship, right? What else do we know before we start crafting an answer? Right, if I'm just talking about pressure and temperature, right, N and V must be constant, right? Which makes sense because otherwise I can't just look at pressure and temperature, right? Okay, so now we have a foundation and we can craft an answer. So we could start by saying, right, what could we start by saying? Right, we could say pressure and temperature are directly proportional, right? As one goes up, the other goes up, or as one goes down, the other goes down. Next, what could we say? Right, we could say what is pressure, right? Pressure is the result of collisions with the walls of the vessel, right? Particles colliding with the walls of the vessel. So then, I think it's easiest to explain from the point of view of changing temperature, right? That works for me. So as we increase my temperature, what happens? Increase the temperature, right? That means my Ke also increases. As the temperature increases and Ke of my molecules increases, they collide with the walls more often and with more force, okay? More often and with more force, which means that if the volume cannot change, the pressure will increase. Yes? All right, all that put together. So pressure and temperature have a direct relationship. As kinetic energy increases, as the temperature increases, the kinetic energy of my molecules increases, which means that they collide with the walls more often and with more force per collision, which, if volume and moles remain constant, results in an increase in pressure because pressure is the result of collisions with the walls of the vessel. And that would be an excellent answer to this question. Okay, next up, it says 3 moles of gaseous carbon tetrachloride occupy a volume of this, right? It says what number of moles is my question, would occupy 12 liters. So liters and liters, let's get some labels here, right? So this would be N1, this would be V1, this would be V2, and this would be N2. So, right, let's go ahead and come up with our relationship, right? And again, if we look here, right, moles and volume, one on top of the other, right? So V1 over N1 equals V2 over N2. Super important. Isolating a denominator is always the most challenging one. So let's go ahead and just isolate it before we plug in stuff, right? So N2 is down here, and we need to get it out of the denominator. So some of you guys like to do the cross multiplying that you learn in middle school, I guess, and that's fine, right? Because that's going to get rid of denominators, which would then give us, right, V1 N2 times V2 N1. And then, bearing in mind that this is what we want to get alone, right, we would divide both sides by V1. So we would have N2 is equal to V2 N1 over V1. Yes? Right. Alternatively, right, we could just multiply by this and then do that. A lot of people's first instinct is going to be to do what? Divide by V2, right? Which means V1 over N1 times V2 is equal to 1 over N2, right? And here, as long as you're paying attention, this is fine, right? As long as you say, ooh, N is in the denominator, that's not what I need, then you can just do what? Right, you can just flip both sides, right? Or do the inverse of both sides, and you get this exact same thing, right? Do you see that? Okay, fantastic. All right, so that's our equation that we need to use. So we have that now. So we have our equation. So now we just get to plug in stuff, right? Making sure our units match. So N2 is equal to V2, which is 12 liters, times N1, which is 3 moles, over V1, which is 25 liters, And as always, right, units make sense. And if we do our math, we get 0.48 moles as my N2. So here we should stop and reason that through, right? 0.48 moles is less than what I started with, but what do we also notice? Right, we decreased my volume, which means we should decrease our N because they're directly proportional. Yes, makes sense? All right, so what we're going to do is we're going to pause here, and then we will pick up in the next video with the rest of our practice problems. All right, thanks for listening. Be good, and I'll see you soon. Bye.